Hi students, today I am coming with a very good derivation, many times asked in the board paper, okay. Capacitance of a parallel plate capacitor. This is the last big topic in this chapter, okay. So we start now. First start with the drawing of a parallel plate capacitor. So first plate and second plate separated by a small gap, and the first plate full of positive charge. So the charge density, it is a sheet, so okay. So surface charge density will be the positive surface charge density, second sheet having negative surface charge density, and we can call like sheet 1 and sheet 2, okay. 1 and 2 you can mark it, and the surface charge density we can label now. So charge density of the first one is plus sigma, charge density of second one is minus sigma. Now gap between the sheets, that we can label like a small letter D, okay. Few more things we have to label now. First thing is how will be the electric field production from the positive charge. Electric field lines will be away from the positive charge. So E1 we can call, because it is produced by first sheet, okay. So upside it is going E1, direction is away from that sheet number 1, okay. So above that sheet we marked E1, below that sheet, that means between the two sheets direction is away from the positive charge. Below the second sheet also direction of the field line from the first one is, first sheet is away from the charged sheet, okay. E1, okay. Now the time to label the field lines due to negative charge. You know the negative charge field line direction will be towards the charge. So from downside E2 is coming towards the negatively charged sheet, in the middle between the sheets coming towards the negatively charged sheet, and from above also coming towards the negatively charged sheet, okay. Now our main labeling over now. Now the three region, can you see? Above sheet, first middle sheet we can write second and then third. Now we can write what is there actually, okay. What is there in the picture? Always write some statement that represent what diagram you made it. It can be your own way, no problem, your own words you can use. Here figure shows a parallel plate capacitor consists of two thin parallel conducting plates. What is there in the picture? I am writing two thin parallel conducting plates having charge densities. What are the charge densities used? Plus sigma and minus sigma. These two charge densities are surface charge densities, and separation between the sheets, so separated by a small distance d, okay. So paragraph making is so simple, right? No need to follow as it is what I wrote here. You can write your own way what you understood from the diagram. So in region 1 and 3, look into region 1 and 3, the top and the bottom. You can see that E1 and E2 are opposite direction, right? So E1 and E2 are equal in magnitude but opposite in direction. Why equal in magnitude I wrote? Because same type charge density, only sign is different. So the net electric field is 0 in region 1 and 3. No more discussion about region 1 and 3, because the net electric field is 0. Got it? Now we look into the middle of that one, that is in region 2. So in region 2 you can see that E1 and E2 are going in the same direction, correct? Look into diagram. So in region 2 the net electric field is equal to, not next, okay, net electric field is equal to E is equal to E1 plus E2. So what we are going to write now? We need the value of E1, we need the value of E2. How we will get it? This is actually linked with the chapter number 1. In chapter number 1 there was an application of Gauss's law, electric field due to a charged thin sheet. This is a charged thin sheet. So we are going to write the expression what we learned from chapter number 1. If you did not watch that one, you can watch that one in the playlist 1. In my video list it is there, okay. So we know that the electric field produced due to a thin sheet is equal to sigma by 2 epsilon 0. Sigma by 2 epsilon 0 for thin sheet. Thick sheet also we derived, but thick sheet not required. Now this is a thin sheet, okay. That is done. So we can start writing total electric field is equal to E1 plus E2. E1 will be sigma by 2 epsilon 0 plus E2 also will be sigma by 2 epsilon 0. This is like the same term added up, right? X plus X format. So 2 into sigma by 2 epsilon 0, 2 cancel. So what left now? Sigma by just epsilon 0, or we can write like 1 by epsilon 0 times sigma. Now E is equal to 1 by epsilon 0 times sigma. We need to get the value of sigma now. From where we will get? 3 type charge densities we studied in chapter number 1. Surface charge density was there. The other two are linear charge density and volume charge density. Right now we required surface charge density because we are considering the sheet. So I am writing that one now. Using surface charge density, sigma is equal to Q divided by A. Yeah, Q divided by A. We are going to apply this value in equation number 1. Okay. So equation number 1 becomes E is equal to 1 by epsilon 0 times in the place of sigma Q by A I wrote. In the place of sigma Q by A I wrote. That's all. Now we are going to write another one expression. So this we are labeling like E is equal to 1 by epsilon 0 times Q by A. Equation number 1, keep safe. What we are going to write now? In the previous video, remember there was one video like 2 videos before, the relation between field and potential. If you did not watch that one, please see my previous video, clearly explain what is the relation between electric field and potential. So we know that the relation between electric field and potential is E is equal to V divided by D. It can be V divided by dr or r. Separation between them is the meaning. So here the diagram showing that separation is D. So E divided by E is equal to V divided by D. Can you look into equation number 1 and 3? In both equation LHS are same. So we are going to equate RHS. So we are going to equate RHS. So expression is E is equal to 1 by epsilon 0 times Q by A. In the place of E, we are going to substitute this equation number 3. So V by D is equal to 1 by epsilon 0 times Q by A. Very easily you can link these two. Now you know that main expression for the capacitor, Q is equal to CV. Q is equal to CV. So we need V now. So how will be that one? V is equal to Q by C. V is equal to Q by C. Substitute now. So the actual expression is V by D is equal to 1 by epsilon 0 times Q by A, right? In the place of V, we are going to substitute Q by C. Already one D is there in the denominator, okay? In the denominator you can see. So you have one option is 1 by D into V you can write. And other option is V into 1 by D you can write. And I prefer to write 1 by D into V. No problem, right? Both are the same. Is equal to right side 1 by epsilon 0 times Q divided by A. Now you can substitute 1 by D into, in the place of V, we can substitute Q by C. So Q by C is equal to 1 by epsilon 0 times Q by A. Almost to finish, you can cancel Q and Q on both sides. And actually our target is to get an expression for C. So take C to the numerator to the right side. And the right side denominator take to the left side. That is the final expression. So right side denominator epsilon 0 A, writing this side numerator now, epsilon 0 A divided by D is equal to C. This is the expression for capacitor. For looking nice, you can do like this one. C is equal to, exchange the LHS and RHS position. C is equal to epsilon 0 A by D. How fast this one, yeah? Just 2 mark question. Rarely asked as 3 mark question, otherwise 2 mark question. Remember, this possibility is more nowadays because there was one more derivation in this lesson, that is the energy stored in a capacitor. Okay, so this steady because number of derivation reduced. Now there is a small modification to this one. Actually the example we are taken is the air filled one. Suppose what happens if a dielectric material is introduced between the plates of the capacitor. Instead of air is the medium between the sheets, the plates. Suppose a dielectric material of dielectric constant K is introduced. Dielectric, I explained in another one video. What is a dielectric? It is basically an insulator, okay? So a dielectric constant, a dielectric material is placed between the sheets of the capacitor. So we can write a statement first. When a dielectric is introduced, okay, when a dielectric is introduced in between the sheets of the capacitor or in the region between the sheet number 1 and 2, okay, or between the plates. So what will happen to the capacitance? So better to memorize this simple concept because we are required to answer MCQ question using this one. So suppose dielectric material is placed between the plates of the capacitor, then what is going to happen is the capacitor will increase K times. Okay, capacitor will increase K times. Okay, now there is another one situation is the gap is filled partially. The previous example what I explained is Suppose the area is, or the gap between the sheet number 1 and 2 is completely filled with the dielectric material of dielectric constant K, then the new capacitance will be K times the original capacitance. Okay, what is that? C dash is equal to K times C. That is previous topic I am talking. Okay, this is a new topic what you are seeing in front of you. This is, suppose the gap is not completely filled. Okay, suppose the parallel plate capacitor partially filled with a dielectric slab, then the equation will be, partially filled meaning is the remaining place, total gap is small letter d, filled gap is T, non-filled gap is D minus T. So new capacitance will be C is equal to epsilon 0 A divided by inside bracket D minus T plus small letter t divided by epsilon r. Okay, where epsilon r is equal to relative. Okay, that's all only. One more topic I added here. Why I added? Because there is no meaning of making one more video for this topic. This is a small topic. Capacitors in series, capacitors in parallel. So that's why I included this topic in this video. So here, like resistors in series, resistors in parallel, you studied in grade 10. A similar topic but not exactly same. Capacitors in series, capacitors in parallel. You know the series connection means chain format connection, right? So let me draw 3 capacitors connected in the form of a chain here and connected across a power supply, that is a potential difference V. And 2 things, small things you want to memorize here. Okay, what is same, what is different in this type of connection. If you are okay with that, your learning completed. So labeled like C1, C2, C3, and potential difference across each capacitor is V1, V2, V3. So remember, in series connection, charge on each capacitor will be same. Whatever it is, one is big, one is small, no matter, charge stored in each capacitor will be same. But potential difference will be separate, different. So always do the calculation for what is different, not for what is same. Since potential difference is different for different capacitor, V is equal to V1 plus V2 plus V3. Total supplied is equal to V1 plus V2 plus V3. So using the expression, you know that Q is equal to CV. So V is equal to Q by C. Substitute in the equation. So in the place of V, we can write Q by C. That is actually the net value. Okay, is equal to, I am not writing Q1 by C1, Q2 by C1 because Q is same. So Q by C1 plus Q by C2 plus Q by C3. Okay, Q you can cancel because it is common everywhere. So what left now? 1 by C is equal to 1 by C1 plus 1 by C2 plus 1 by C3. We can label this 1 by C is 1 by Cs. Okay, that's all finished. So in series connection, what is the conclusion is, reciprocal format we are getting the effective capacitance of the capacitors connected in series. Now we come to the parallel connection. This is a parallel connection. There are 3 capacitors considering now for parallel connection, labeling now C1, C2, C3 and connected across a power supply. Okay. The same picture we used in grade 10 for resistance. This is for capacitors. And here the similar thing, same we want to write. What is different we want to write? You know that parallel connection is a connection where potential difference will be same. So in parallel connection you can write charge is different. Series connection charge is same, parallel connection charge is different, but potential difference is same. So we will not work for potential difference now. We will do the total calculation for charge. Whatever supplied from the power supply, that will be equal to charge stored on first plus charge stored on second plus charge stored on third capacitor. So Q is equal to, we can write like Q is equal to Q1 plus Q2 plus Q3. Okay. Now this is the time to use the equation using Q is equal to CV. The same expression what we used to left side. So directly, because Q is equal to CV only. So CV is equal to C1 V1 not writing, okay, because V is same. So C1 V plus C2 V plus C3 V. V is common everywhere, so cancel V. So C is equal to C1 plus C2 plus C3. We can label what is that main C. Main C is actually CP. So CP is equal to C1 plus C2 plus C3. So simple, right? So series and parallel connections are actually directly less chance of asking, but we may ask in the numericals. Okay. One more topic here also clearly mentioned in the syllabus that qualitative study only, no need derivation, no need depth discussion. Okay, detailed discussion not required. So energy stored in a capacitor is U is equal to half CV square. Energy stored in a capacitor is U is equal to half CV square. 2-3 ways you can write the same expression using Q is equal to CV expression substitution. So first I am substituting one format, okay. One format is Q is equal to CV, right? So left side you see V is equal to Q by C. So in the place of V I am going to apply now. So 1 half C V square is Q by C whole square. So taking the square separately is Q square by C square. So Q square divided by 2C. That's all. That's all, yeah. So another one format for the expression is U is equal to Q square by 2C. First one is U is equal to half CV square. Remember, that is our standard equation to remember. Other equation only to remember all the time. Whenever you required, just write Q is equal to CV and try to substitute. Answer will form. So what is directly given is half CV square I gave you. Then later after substituting V is equal to Q by C, we got a format U is equal to Q square by 2C. One more format trying to make, that is C is equal to Q by C going, C is equal to Q by V going to apply. C is equal to Q by V going to apply. So applied, then found that U is equal to half QV. See, you can see in the picture, in the place of C I applied Q by V and V square cancelled, right? After that half QV. So the three forms we can write like this one. First thing is U is equal to half CV square. Second format is U is equal to Q by 2C. Third format is U is equal to half QV. All are representing the same thing. What is the same thing? Energy stored in a capacitor. Okay, useful for numerical. So that's all. I hope manageable length only the video. Okay, anyway I covered the main things. By this we are covering all the derivations, theory, concept of chapter number 2. The remaining videos will be based on the board numericals related to chapter number 2. So we will do numerical in next video. Okay students, thank you. Have a nice day. Bye bye.